Hello and welcome. This is Chapter 5, Section 5, Part A on the Law of Sines. These are what we're going to be learning about today and on the next lesson as well. So how about you try this as a discovery thing and notice that we have A is across from little a. So we're going to have this as little a. B is across from little b, and C is across from little c, or lowercase c. We're going to set up those ratios, make sure your calculator is in degrees. Try this and see what you notice. So after you just finish that warm-up, the law of sines is essentially saying that if I have the sine of angle A over its opposite side length, well, that's going to be the same ratio as the sine of angle B over its opposite side length, and is equal to the sine of angle C over its opposite side length. And this actually works for every triangle we have. So it can work for right triangles or non-right triangles. So what we're going to do next is use the law of sine to solve a triangle, which means find everything that's missing. So the first step is just fill in the information we have. So A is 116 degrees. We know that C is 25 degrees. Well, we can find the last angle of a triangle very easily by just saying, well, angle B is going to be equal to 180 degrees, and we're going to both subtract the 116 and subtract the 25 degrees to get that angle B is in fact 39 degrees. So that's answer numero uno. Now, we do know that little a is 51. So we're going to have to use that. With the law of sine, you have to have an opposite angle and an opposite side length. So we have to have stuff that is across from each other in order to set up the law of sine to find other information. You also need one other piece of information, either one other angle or one other side in order to do this. So you need three things of information, and you have to have something that is opposite of each other. So let us set up our first ratio. So we have the sine of 116 degrees, and we have something that is across from it, which is 51. So this ratio will be something else, which let's go in order, or not in order. Let's find A or B. It doesn't matter, sorry, B or C. It doesn't really matter which way we go. So if we wanted to find B first, we can say the sine of that 39 degrees over the little b. Now, we can just cross multiply. That's what we usually do, and people like to do it that way. So it's like b times the sine of 116 degrees is equal to 51 times the sine of that 39 degrees. Now, we just have to divide both sides by the sine of 116 degrees. Remember, on a calculator, when you type this all in on a calc, just make sure you have the mode in degrees or use the degree symbol. So when you do this, you should get that little b is roughly 35.709. So now we have capital B, which is this 39. And then we have little b, which is 35.709. So let's find our last thing, which is little c. So let's do it in a different color here. So little c, which is here, which is across from capital C. So we have the sine of capital C, which is 25 degrees, over the little c. And then we're going to use the same ratio of sine of 116 over the 51. We're going to keep using that. So this is how we're going to set up and start with everything. So we still have that. The only difference from finding C and B is that you have sine of 39 over B, you have sine of 116, sorry, sine of 25 over C. And then you're going to essentially do exactly the same steps. We cross multiply, and then we end up getting C will be approximately 23.981. So that would be solving this triangle. We have B, C, and capital B. So we're going to talk about the law of sine in an ambiguous case where there might be a time where you could create two different triangles. So if I have this set up, I'm going to first start by just drawing this little kind of right angle dash line here. This is kind of the height of the triangle, no matter where it is. So what's interesting is that if I create a length for A here, let's say this is whatever A length, I could create the same length here that are exactly the same length here. And that would create two different types of triangles. an obtuse and an acute triangle. So like the first one, if we have, let me go this, we can have A, B, C, this triangle, which is an acute triangle. So this whole triangle here has acute angles for all of them. Or we could create what's called an obtuse triangle, which would be in here, this triangle right here. So we either have B where it's an obtuse angle, or we have B where it's an acute angle. And by the way, if you find the acute angle, to find the obtuse angle, just do 180 minus this to find the other triangle. So we're not going to really focus on this too much, but there are two specific cases that could happen if you're only given measures of angles and side lengths. So let's do another example here before I let you try one and we're done for the day. Again, I'm just going to randomly draw a triangle. So like just draw a triangle. I don't care if it's acute, obtuse, or whatever. I'm just going to put A, B, and C down. It's just kind of a visual aid. We have little a, which is 12. We have little c, which is 9. And then we have capital A, which is 40 degrees. So I just like to generically draw a triangle. I don't know if it's obtuse, acute, or whatever. But it is important that we draw the A across from the A and the B across from the B and C across from C. So what we're going to do is notice that we have an angle, and two side lengths. We do have this angle across from that, so that is our first thing to note, that those are across from each other. And we know that this 9 is across from this C, so we're probably going to use those two. So let's say the sine of angle C over 9 is equal to that sine of 40 degrees over the 12. Now we can solve this by cross multiplying if we want, but it's just easier if we just multiply this 9 to both sides where that one reduces, so that we have the sine of angle C is equal to this sine of 40 degrees times 9 all over 12. Now you could figure that out as a decimal if you want. It's like 0.4820907 if you have it in degrees. But we don't need to do that. What we need to do is we're looking for capital C, which we're just going to take the inverse sine of both sides here. So if I take the inverse sine to find an angle of that, you put this all in parentheses, and then you do sine of 40 degrees, close that parenthesis, times 9, divide by 12. You should get that. We get C degrees. Remember, those ones will reduce. We'll get C degrees is about, in this case, 28.822 degrees. So we will leave all of those decimals in here, so we're not going to round it off if we use C again at some other point, which we might. But what we're going to do is find our last angle. So we know that C is this 28.822. Now we can find B very easily by just doing the idea of 180. So angle B here is equal to 180 degrees minus both A and C, which will give us an approximate angle of 111.178 degrees roughly for angle B. Now again, on your calculator, I will just keep this. You can copy and paste the whole decimal and all the digits when you do that, so that when you use angle B to find a little b, you'll be able to have that as an exact answer, and then you can round it later. So the last step then is to find, well, if we have the sine of angle B here, which is that 111.17, and you would keep all of the decimals, which is like 7, 9, 6, 1, 3, keep all of those decimals all over little b, and that's equal to the sine of, well, we're still going to do 40 over 12. And now we can cross multiply and solve like we did on the other side, and then you should get that b is about 17.408. And that would be how we would solve this triangle. How about you take the time to try to solve this? I will just have the answers in a moment, so pause it. I will have some answers shortly. So hopefully you tried it and you got these three answers. This one's pretty easy, 180 minus the other two. Then set up the sine ratios, and again, make sure you're using degrees. Just to kind of wrap up this lesson and conclude, we have SOHCAHTOA. It helped us handle right triangles, but this law of sine is going to take us further because we can connect all of the triangles with this one ratio. So makes it a lot easier, not just right triangles.